January 5th, 1943. Dawn breaks over the waters off Guadalcanal. Lieutenant Red Cochran, commanding the after 5-inch battery aboard the light cruiser USS Helena, watches 4 Japanese Aichi D-3A Val dive bombers break through the morning haze, their distinctive fixed landing gear silhouettes unmistakable against the brightening sky. One scores a hit on the New Zealand cruiser Achilles before the group wheels around to escape. Standard procedure would be to let them go. They're already pulling away at 300 miles per hour, climbing hard, presenting the kind of crossing shot that requires 2,500 rounds on average to score a single hit. But Cochran's guns aren't loaded with standard ammunition. His crews slam 3 rounds into the breeches, weapons that look identical to every other 5-inch shell in the Pacific Fleet, but carry something inside that's about to change naval warfare forever. The first 2 shells scream out at 2,600 feet per second. They don't hit the fleeing bomber. They don't need to. 15 feet from the aircraft, something impossible happens. The shells sense the metal fuselage rushing past and detonate on their own. The Val disintegrates in a cloud of shrapnel and fire. The crew never knew what killed them. Neither did the Japanese High Command, because what just happened shouldn't have been possible. A 5-inch artillery shell contains no room for the electronics needed to sense a target. The shock of firing generates 20,000 times the force of gravity, enough to pulverize any radio or detection system into dust. Miniature vacuum tubes capable of surviving that acceleration don't exist. Except they do. And they're about to turn America's anti-aircraft defenses from a desperate gamble into a highly effective weapon so powerful that Japanese pilots will start flying one-way missions because conventional attacks have become mathematically impossible. This is the story of the proximity fuse, the billion-dollar secret that saved more American lives than almost any other invention of World War II, and the scientists who built something the enemy thought was science fiction. The problem that would nearly cost America the Pacific War started at Pearl Harbor on December 7, 1941. The USS Helena took a torpedo hit that morning, one of many ships damaged or destroyed by Japanese aircraft that appeared with devastating suddenness. As shipwrights patched the 18-foot hole in her hull over the following months, naval analysts studied a more fundamental problem that no amount of welding could fix. American anti-aircraft gunnery was catastrophically ineffective. The numbers were brutal and undeniable. Against a maneuvering aircraft at combat speeds, a 5-inch .38 caliber gun, the Navy's primary anti-aircraft weapon, required an average of 2,500 rounds to achieve a single kill. 2,500 shells, each weighing 55 pounds, each costing $18 to manufacture. To destroy one aircraft. The mathematics were simple and terrifying. A Japanese Val dive bomber cost roughly $15,000. Shooting it down cost $45,000 in ammunition alone, assuming perfect logistics and unlimited time to fire. Neither existed in combat. The fundamental problem was physics, unforgiving and absolute. An aircraft moving at 300 miles per hour covered 440 feet every second. A 5-inch shell left the gun at 2,600 feet per second, which sounds instantaneous until you calculate actual engagement distances. Against a target at 4,000 yards, over 2 miles away, the shell needed 4.6 seconds to arrive. In those 4.6 seconds, the aircraft moved over 2,000 feet. Gunners aimed at where the aircraft was. The shell arrived at where the aircraft had been, passing through empty air while the target flew on untouched. 2 solutions existed. Contact fuses required hitting the target directly, threading a 55-pound projectile through space to intersect with a 20-foot wingspan, moving at combat speeds. The odds were astronomical. Time fuses required gunners to calculate exactly when the shell would reach the target's future position, set a mechanical timer by hand, and pray their calculations were correct. If they were off by half a second, the shell exploded hundreds of feet from the target, harmlessly scattering shrapnel through empty sky. Both methods failed consistently. Japanese aircraft pressed their attacks home because they knew the odds favored them. American ships were lost because their guns couldn't hit back effectively. The British understood this problem first. By 1939, with war already consuming Europe, researchers at the Telecommunications Research Establishment were investigating something that sounded like fantasy. Could a shell be built that knew when it was near a target? Samuel Curran, William Buteman, and their colleagues explored every possible detection method. Optical systems using reflected light, acoustic systems listening for engine noise, magnetic systems sensing metal, capacitive effects detecting changes in electrical fields. Every approach hit the same wall. The electronics required to detect targets and trigger detonation were too large, too fragile, and too complex to survive being fired from a gun. The shock of acceleration shattered vacuum tubes. The spinning generated by rifled barrels, 25,000 revolutions per minute, tore components apart. Moisture infiltrated sensitive circuits. The technology seemed impossible. British researchers made progress on fuses for bombs and rockets, weapons that experienced gentle acceleration and didn't spin. But projectiles fired from guns remained beyond reach. When the Tizard mission arrived in the United States in September 1940, carrying Britain's most sensitive technologies, including cavity magnetron radar designs, they shared their proximity fuse research as well. The message was clear. The concept works in theory, but building a gun-fired version might be impossible during this war. The U.S. Navy didn't accept impossible. In June 1940, Vannevar Bush, director of the newly created National Defense Research Committee, asked every service for their most urgent technical needs. The Navy's request went straight to the top of the list. Give us a proximity fuse that works in 5-inch shells. Everything else is secondary. The assignment went to Section T of the NDRC's Division 4, a group of physicists, engineers, and ordnance specialists led by Dr. Merle Fuze at the Carnegie Institution in Washington. Fuze, a 40-year-old physicist who'd pioneered radar research in the 1930s, understood they were being asked to miniaturize an entire radio transmitter receiver system into a space the size of a pint milk bottle, make it survive 20,000 G-forces, ensure it worked in temperatures from 100 degrees to 50 below zero, give it a power supply that functioned after violent acceleration and spinning. Build in safety mechanisms so it didn't explode in storage or kill friendly aircraft, add a self-destruct feature to prevent enemy capture, and mass-produce it by the millions. The timeline was impossible. The technical challenges were insurmountable. Failure meant watching American sailors suffer losses because their guns couldn't protect them. Success meant rewriting the rules of aerial warfare. Dr. James Van Allen, who would later discover Earth's radiation belts, joined the Applied Physics Laboratory in early 1942. The laboratory itself was created specifically to manage proximity fuse development, housed at Johns Hopkins University under cover so tight that the university's board of trustees weren't told what the million-dollar military contract was actually funding. Van Allen's assignment was developing vacuum tubes that could survive being shot out of a gun. The problem seemed simple until you understood the forces involved. When a 5-inch shell fired, it accelerated from 0 to 2,600 feet per second in the length of the gun barrel, roughly 20 feet. That acceleration generated forces exceeding 20,000 Gs. A vacuum tube weighing 1 ounce experienced pressures equivalent to 1,200 pounds trying to crush it. The glass envelopes shattered, the filaments snapped, the internal elements distorted and failed. Standard radio tubes disintegrated instantly. Van Allen and his team started with miniature tubes designed for hearing aids, the smallest vacuum tubes commercially available. Western Electric and Raytheon provided samples. The tubes were smaller than a man's thumb. Delicate glass cylinders containing wire filaments and metal grids spaced by thousandths of an inch. The researchers built test fixtures that simulated gun firing, using compressed air to accelerate the tubes at extreme G-forces. Every test ended with broken glass and ruined components. They redesigned the tube's internal structure, shortening the elements to reduce leverage that caused bending. They used thicker filament wire that wouldn't snap under stress. They changed the glass composition to something harder, more resistant to shattering. They filled the tubes with special mounting compounds that cushioned the internal elements. Each modification required building new tubes, testing them to destruction, analyzing the failures, and trying again. Months passed. Hundreds of design iterations failed. The project consumed resources at a staggering rate, but the Navy kept funding it because the alternative was watching their ships burn. By January 1942, they had a prototype tube that survived test firing. The T3 Fuze, built around these rugged miniature tubes, faced its first real test that August. The light cruiser USS Cleveland, fresh from commissioning and conducting shakedown trials in Chesapeake Bay, loaded proximity-fused shells into her 5-inch batteries for evaluation. The test was scheduled for 2 days. Navy observers expected to fire hundreds of rounds to evaluate effectiveness. The targets were 3 radio-controlled drones, small aircraft flown remotely at varying speeds and altitudes. Cleveland's gunners opened fire at the first drone. 4 shells screamed out. The drone was destroyed. The second drone maneuvered evasively. The gunners tracked it smoothly and fired again. The drone fell from the sky. The third drone never had a chance. The Navy canceled the remainder of the test because there were no targets left. The impossible had become real. Production authorization came immediately. 5 companies, Crosley Corporation, RCA, Eastman Kodak, General Electric, and McQuay Norris, began manufacturing fuses using miniaturized glass vacuum tubes from Sylvania. The scale-up was brutal. Each fuse required 24 precision components machined to tolerances of thousandths of an inch. The miniature tubes had to be individually tested because a single bad tube meant a fuse that failed in combat. Assembly required careful handwork by trained technicians, most of them women who'd never seen the inside of an electronics factory before Pearl Harbor. Initial production in November 1942 reached 500 fuses per day. Everyone was immediately shipped to Mare Island Naval Ammunition Depot in California, inserted into 5-inch shells, and forwarded to Pearl Harbor. The shells went to 3 ships, USS Enterprise, USS Saratoga, and USS Helena. Personnel aboard all 3 received intensive training in the new weapons' capabilities and strict security protocols. The fuses were classified above top secret. Sailors were told that discussing them with anyone, including other crew members not directly involved with the guns, was grounds for court-martial. The technology absolutely could not fall into enemy hands. If the Japanese or Germans recovered an intact fuse and reverse-engineered it, they could build their own versions. German flak batteries equipped with proximity fuses would inflict devastating losses on Allied bomber formations. The strategic bombing campaign might collapse. The Pentagon initially refused to authorize any use where a dud shell might land on enemy territory. Commander William Parsons, the Navy ordnance specialist who shepherded the first Fuze shipment to the Pacific, would later arm the atomic weapon aboard Enola Gay at Hiroshima. In early January 1943, he watched as Helena's gunners loaded the new ammunition and waited for combat to test what the laboratories had promised. The test came at dawn on January 5th, when those 4 Val dive bombers appeared. Lieutenant Cochrane's 3 shells performed exactly as designed. The radio transmitter in each fuse sent out pulses at 220 megahertz. When reflected pulses bounced back from the metal aircraft, the fuse measured the changing frequency caused by the Doppler effect as target and shell closed on each other. At precisely 15 feet distance, when the returning signal reached a predetermined threshold, indicating optimal lethal radius, a tiny amplifier circuit closed, firing a detonator that ignited the 7 pounds of high explosive in the shell's body. The Val bomber was engulfed in a sphere of shrapnel moving at thousands of feet per second. The aircraft didn't just crash. It disintegrated in mid-air, transformed from a functioning machine into falling debris in less time than a human eye could register. The other 3 bombers escaped that morning, but the technology had been proven in combat. The weapon that shouldn't exist had just killed its first enemy. The impact was immediate and measurable. In 1943, Navy ships in the Pacific fired 36,370 anti-aircraft rounds. Only 25% used proximity fuses. Supplies were still limited and security restrictions tight. But those 25% accounted for 51% of all aircraft kills. The fuses were 3 to 4 times more effective than conventional ammunition. The lethal fragment area of a proximity-fused shell was 3,000 square feet, compared to 60 square feet for a time-fused shell. One analysis estimated that 278 Japanese aircraft were destroyed by proximity-fused shells between 1943 and the war's end. Using conventional ammunition, only 46 of those would have been shot down. The difference represented over 200 aircraft that reached their targets versus 200 aircraft destroyed before they could attack. That difference meant American ships that survived instead of being lost, American sailors who lived instead of becoming casualties. As production ramped up through 1943 and into 1944, the fuses became standard equipment throughout the Pacific Fleet. By late 1943, manufacturers were producing 40,000 fuses per day. By war's end, daily production reached 70,000 fuses. More than 22 million were manufactured total, requiring over 100 companies and 80,000 workers. The scale of American industrial production was staggering and unstoppable. The technology proved itself repeatedly in the desperate naval battles of 1944 and 1945. When Japanese forces launched kamikaze attacks, proximity fuses became the primary defense against aircraft that accepted their own death as inevitable. Traditional ammunition struggled against kamikazes because the pilots intentionally flew through defensive fire, willing to absorb damage as long as their aircraft remained controllable long enough to reach the target. Proximity-fused shells didn't need to eliminate the pilot or destroy the aircraft's controls. They simply needed to pass near enough to detonate and break the aircraft into pieces too small to reach their target. Admiral Arleigh Burke, who served as Chief of Staff to Admiral Mark Mitcher, commanding the fast carrier task forces, witnessed the fuse's effectiveness firsthand. Years later, he stated flatly that without proximity, fuses, American ship losses, and casualties in the last half of the Pacific War would have been enormously larger. The fuses brought down enemy planes by the dozens. Secretary of the Navy James Forrestal called them indispensable, crediting them with blazing the trail to Japan. Without the protection proximity fuses provided, the westward push across the Pacific would have been slower and cost immeasurably more in American lives. On May 11, 1945, during the Battle of Okinawa, a group of American destroyers and landing craft faced a 90-minute attack by 156 Japanese aircraft on one-way missions. The destroyers, USS Hadley and USS Evans, equipped with proximity-fused ammunition, accounted for 35 confirmed takedowns before being hit multiple times and forced to withdraw. The official Navy report called the fuses indispensable to survival. Without them, both ships would have been lost in the first minutes of the attack. The Pentagon's absolute prohibition on using proximity fuses over land persisted through 1943 and most of 1944. The risk of a dud shell falling into enemy hands was considered too great. Then Germany launched the V-1 flying bomb campaign against London in June 1944. The V-1, a jet-powered cruise missile loaded with nearly 2,000 pounds of explosives, flew at 400 miles per hour at low altitude, too fast for most conventional interceptors to catch consistently. British anti-aircraft batteries, concentrated in a coastal strip to protect London, faced the same problem American ships had confronted. Their guns couldn't hit fast, small targets reliably. On June 12, 1944, the U.S. authorized proximity fuse use over England. The V-1s flew over water before reaching land, meaning dud shells would fall into the sea rather than territory the Germans could access. Within days, the results were dramatic. From the first day of V-1 attacks through the end of August, Germany launched 9,300 flying bombs, an average of 120 per day. By the end of the fourth week, using proximity fuses, anti-aircraft batteries were stopping 79% of all incoming V-1s. The fuses saved London. Thousands of British civilians owed their lives to shells that exploded near rather than needing to hit directly. Winston Churchill, who'd pushed hard for proximity fuse development from the British side, acknowledged their critical role. These American-made fuses, he said, proved potent against the unmanned aircraft terrorizing England. The final test came in December 1944. When Germany launched the Battle of the Bulge on December 16th, General Dwight Eisenhower immediately demanded authorization to use proximity-fused artillery shells against German ground forces. The Pentagon resisted. German troops might capture unexploded shells from the snow-covered forests of the Ardennes. The technology would be compromised. Eisenhower insisted. His artillery commanders had been training with fuses designed for airburst detonation over ground targets, shells that sensed the Earth's surface and exploded at predetermined heights, 20 to 50 feet up, showering troops and vehicles with shrapnel from above. Without those shells, his forces might not stop the German offensive. Authorization came within 2 days. Colonel George Axelson, commanding the 406th Artillery Group, didn't wait for official permission. When the lightly armed 38th Cavalry Squadron called desperately for fire support on the morning of December 16th, he ordered his gunners to load the new shells despite restrictions. The decision likely prevented heavy casualties among American forces. 200,000 proximity-fused shells were used in the Battle of the Bulge and the Allied advance that followed. The effects were devastating beyond anything German forces had experienced. Traditional artillery shells exploded on impact with the ground. Soldiers in foxholes, behind cover, or in trenches had significant protection. Proximity-fused shells exploded in the air above them. There was no protection, no shelter, no way to take cover. The shrapnel rained down from above, finding soldiers who thought they were safe. German prisoners described the attacks as quick, powerful bursts against which there was simply no defense. Some units experienced what amounted to refusal to follow orders. Soldiers refusing orders to move during American artillery barrages because staying meant facing overwhelming danger. General George Patton wrote enthusiastically to the War Department. "The new shell with the funny fuse is devastating," he reported. "We caught a German battalion trying to cross the Sauer River with a battalion concentration and stopped by actual count 702. I think when all armies get this shell, we will have to devise some new method of warfare. I am glad you all thought of it first." "The funny fuse," Patton later declared, "won the Battle of the Bulge." From the Battle of the Bulge through the crossing of the Rhine, proximity-fused anti-aircraft fire brought down more than 1,000 German aircraft. Luftwaffe attacks, already diminishing under overwhelming Allied air superiority, became extremely hazardous when proximity-fused shells turned the sky over Allied positions into an impenetrable defensive zone. The Germans knew something had changed. Captured prisoners described American artillery shells that exploded with uncanny precision above ground. Luftwaffe pilots reported American ships whose anti-aircraft fire seemed impossibly accurate. Intelligence officers collected reports, but couldn't explain what they were hearing. During the Battle of the Bulge, German forces overran an American ammunition dump containing 20,000 proximity fuses. They captured them intact, crated, and ready for use. German ordnance specialists examined the shells but concluded they were simply time fuses with unusually sophisticated mechanisms. The concept that a radio transmitter receiver could survive gunfiring remained so far outside their understanding that they never realized what they possessed. Germany had actually researched proximity fuses extensively in the late 1930s. Rheinmetall-Borsig developed designs using electrostatic fields. Other firms explored acoustic triggers and radio methods. More than 30 different designs were investigated, but in 1940, Hitler issued a directive that effectively killed these programs. Only projects that could reach production within 6 months were to continue. Everything else was terminated to focus resources on immediate needs for the invasion of the Soviet Union. German scientists abandoned their magnetron and microwave radar programs at the same time. The decision cost them technologies that might have changed the war's outcome. By 1945, German engineers had resumed proximity fuse development with prototypes designated Kuhglockchen for 88mm shells and Kuhglocke for 128mm shells. Trial firings at Kummersdorf testing grounds showed promise. Series production was scheduled for March 1945. It never happened. The war ended first, and German forces never fielded proximity fuses in combat. The technology that Section T developed under Dr. Fuze's direction represented more than just miniaturized radios in artillery shells. The project integrated civilian and military scientists in unprecedented ways, opened communication lines with British researchers, and demonstrated that American industrial capacity could scale impossibly complex technologies to mass production in time frames that defied pre-war expectations. 3% of all physicists in the United States worked on the proximity fuse at the project's peak. The total cost exceeded $1 billion, equivalent to over $15 billion today. Only the Manhattan Project commanded more resources and attention. The comparison was appropriate. Both projects were considered essential to Allied victory. Both operated under extraordinary secrecy. Both succeeded because failure was unacceptable. The legacy of the proximity fuse extends far beyond World War II. Modern air defense systems, from ship-mounted phalanx, CIWS, to Patriot surface-to-air missiles, use proximity fusing as standard. The Phoenix AIM-54 air-to-air missile, standard SM-1 and SM-2 surface-to-air missiles, and essentially every guided weapon developed since 1945 incorporates descendants of the technology Van Allen and his colleagues pioneered. The principle remains unchanged. Detect when you're near a target and detonate at optimal distance for maximum effect. The execution has advanced beyond what those wartime engineers could have imagined, but the core concept they proved possible under impossible conditions remains fundamental to modern warfare. Lieutenant Cochrane, whose 3 shells fell the Val bomber off Guadalcanal on January 5, 1943, never saw the fuses he fired. They were sealed inside the shells, classified technology he wasn't authorized to examine. He knew his ammunition was special, that it worked differently from standard shells, that discussing it could result in court-martial. He didn't know he was firing miniature radar sets, vacuum tubes that survived 20,000 G-forces, electronics that functioned in a package smaller than a pint bottle while spinning at 25,000 RPM and surrounded by 7 pounds of high explosive. He just knew his guns finally worked the way they were supposed to. Point at the enemy. Fire. Watch them fall. The simplicity was deceptive. Behind that simple effectiveness lay years of research, hundreds of failed prototypes, industrial mobilization across 5 major manufacturers and over 100 subcontractors, 80,000 workers, 3% of America's physicists, and $1 billion. The proximity fuse took everything impossible about the problem and made it routine. That transformation, from impossible to routine, from theory to 22 million manufactured units, represented American industrial and scientific capability operating at levels the Axis powers never matched. The funny fuse, as Patton called it, turned anti-aircraft gunnery from desperate hope into reliable lethality. It protected American ships that carried the war across the Pacific. It saved London from the V-1 onslaught. It decimated German forces during the Battle of the Bulge. And it did all of this without requiring gunners to actually hit what they were shooting at. The shell just needed to pass close enough for the tiny radar inside to whisper, "Now." In that whisper, carried by radio waves reflecting from enemy metal, lay victory measured in American lives saved and enemy forces neutralized. The shell that didn't have to hit the target proved more effective than any weapon that required direct contact. Physics, engineering, and American industrial might combine to create something the enemy thought was impossible. And that impossible weapon, shrouded in secrecy and manufactured by the millions, helped win the war.